Hello students, welcome to the channel. In this video, we'll solve the fourth and final reading passage of the December 2019 ACT Form C03, the natural science passage. This passage is adapted from the article Reinventing the Leaf by Antonio Ricaldo. Nathan Lewis has been giving a lecture on the energy crisis that is both terrifying and exhilarating. To avoid potentially debilitating global warming, the chemist says civilization must be able to generate more than 10 trillion watts of clean, carbon-free energy by 2050. That level is 3 times the US's average energy demand of 3.2 trillion watts. Before Lewis's crowds get too depressed, he tells them there is one source of salvation. The sun pours more energy onto the earth every hour than humankind uses in a year. But to be saved, humankind needs a radical breakthrough in solar fuel technology, artificial leaves that will capture solar rays and churn out chemical fuel on the spot, much as plants do. We can burn the fuel as we do oil or natural gas to power cars, create heat or generate electricity, and we can store the fuel for use when the sun is down. Lewis's lab is one of several that are crafting prototype leaves, not much larger than computer chips, designed to produce hydrogen fuel from water rather than the glucose fuel that natural leaves create. Unlike fossil fuels, hydrogen burns clean. Other researchers are working on competing ideas for capturing the sun's energy, such as algae that has been genetically altered to pump out biofuels, or on new biological organisms engineered to excrete oil. All these approaches are intended to turn sunlight into chemical energy that can be stored, shipped, and easily consumed. Lewis argues, however, that the man-made leaf option is the most likely to scale up to the industrial levels needed to power civilization. So this passage is about the need for a renewable energy source, and particularly being able to capture solar energy into these artificial leaves, which, like real leaves, will be able to capture sunlight, but unlike real leaves, will produce water, which can then be burnt to produce hydrogen. And that is the most promising technology that can come out of this process. Although a few lab prototypes have produced small amounts of direct solar fuel or electrofuel, as the chemicals are sometimes called, the technology has to be improved so the fuel can be manufactured on a massive scale very inexpensively. To power the US, Lewis estimates the country would need to manufacture thin, flexible solar fuel films instead of discrete chip-like devices that roll off high-speed production lines the way newsprint does. The films would have to be as cheap as wall-to-wall carpeting and eventually cover an area the size of South Carolina. Far from being a wild dream, direct solar fuel technology has been advancing in fits and starts ever since President Jimmy Carter's push for alternative energy sources during the 1970s oil shocks. Now, with the new energy and climate crunch looming, solar fuel is suddenly gaining attention. So this talks about how this technology has been in play since the 1970s, but one aspect which has hindered its progress is the cost, right? We need to be able to produce it at scale and inexpensively. And that may now be possible with this idea of the artificial solar leaf. In photosynthesis, green leaves use the energy in sunlight to rearrange the chemical bonds of water and carbon dioxide, producing and storing fuel in the form of sugars. We want to make something as close to a leaf as possible, Lewis says, meaning devices that work as simply, albeit producing a different chemical output. The artificial leaf Lewis is designing requires two principal elements: a collector that converts solar energy, photons, into electrical energy, electrons, and an electrolyzer that uses the electron energy to split water into oxygen and hydrogen. A catalyst, a chemical or metal, is added to help achieve the splitting. Existing photovoltaic cells already create electricity from sunlight, and electrolyzers are used in various commercial processes. So the trick is marrying the two into cheap, efficient solar forms. Bulky prototypes have been developed just to demonstrate how the marriage would work. Engineers at a Japanese automaker, for example, have built a box that stands taller than a refrigerator and is covered with photovoltaic cells. An electrolyzer inside uses the solar electricity to break water molecules. The box releases the resulting oxygen to the ambient air and compresses and stores the remaining hydrogen, which the automaker would like to use to recharge fuel cell cars. In principle, the scheme could solve global warming. Only sunlight and water are needed to create energy. The byproduct is oxygen, and the exhaust from burning the hydrogen later is in a fuel cell is water. The problem is that commercial solar cells contain expensive silicon crystals, and electrolyzers are packed with platinum, to date the best material for catalyzing the water splitting reaction, but it costs $1,500 an ounce. So these last couple of paragraphs explain the chemical reaction involved in generating hydrogen fuel renewably. And the only crunch there is the cost, right? The cost of electrolyzers, which are made of platinum, as well as the solar cells that contain silicon. Lewis calculates that to meet global energy demand, future solar fuel devices would have to cost less than $1 per square foot of sun collecting surface and be able to convert 10% of that light energy into chemical fuel. Fundamentally new, massively scalable technologies such as films or carpets made from inexpensive materials are needed. 31, the main function of the 7th and 8th paragraphs, line 65 to 82. So we are looking at this part, right? So this is what has been done by the Japanese automaker and what needs to be done to kind of bring the cost down. So this suggests that solar technology is advanced but still faces problems that prevent it from being a viable power source on a large scale. Introduce the information that under specific laboratory conditions, electrolyzers can be used to release energy. Establish that the US and Japan are collaborating on research. Question whether the auto industry will be a leader. So it's A, right? You're giving examples of the advances that have happened, but the challenges that remain to produce solar energy on scale. Based on the passage, whose opinion is it that there is a need for more than 10 trillion watts of clean carbon-free energy by 2050? So this, right? The chemist says that civilization must be able to generate more than 10 trillion watts of clean carbon-free energy. So the chemist is Lewis himself. So this would be researchers in South Carolina, an unidentified chemist whom Lewis challenges in his lecture. Lewis, as expressed in lectures he gives on the subject of world energy needs, so it's H. The author before attending a lecture, so it's H. Based on the passage, what is the relationship between the radical breakthrough referred to in line 12 and the capabilities discussed in lines 14 to 17? So, radical breakthrough. Humankind needs a radical breakthrough in solar fuel technology, artificial leaves that will capture solar rays and churn out chemical fuel on the spot. We can burn the fuel as we do oil or natural gas to power cars, create heat or generate electricity, and we can store the fuel for use when the sun is down. So lines 14 to 17 give the possible applications of the radical breakthrough, right? So both were made possible as a result of Lewis's work in his lab. Both serve as examples for Lewis of the energy industry's misguided focus on consumption. The breakthrough will make the capabilities possible. The breakthrough has been made based on the capabilities. So it's C, because the capabilities will come when the breakthrough happens. According to the passage, one challenge facing Lewis in developing his energy solution is the high price of the silicon crystals and platinum that are integral to the process, lack of technology to split water into hydrogen and oxygen, diminishing availability of federal funding for his research, public's reluctance to embrace new technology. So it's F, right? We know that all the systems are in place, but the problem stems from the high price of the silicon crystals and the platinum that is used in electrolyzers. According to Lewis, compared to the amount of energy the sun pours onto the earth in 1 hour, what amount of energy does humankind use in 1 year? So this comes from here that the sun pours more energy onto the earth every hour than humankind uses in a year. So the amount of energy the sun pours in comparison to this, what amount of energy does humankind use? So it is a smaller amount. It uses a smaller amount than the amount that the sun pours every hour onto the earth. According to the passage, what size are the prototype leaves being developed in Lewis's lab? About the size of a human hand, the size of a maple leaf, not much larger than a carpet square, not much larger than a computer chip. Okay, so let's see, this was here. Not much larger than computer chips, right? So it's a J. As used in line 25, the phrase pump out most nearly means. Okay, so this is the phrase, so let's read this. Other researchers are working on competing ideas for capturing the sun's energy, such as algae that has been genetically altered to pump out biofuels. So to produce, right? That's the best word. To produce biofuels, not to drain or to remove, and to siphon is to kind of direct it in another direction. So that doesn't make sense here. According to the passage, what physical form does Lewis imagine his artificial leaves will ideally take? Chip-like devices, thin flexible films, rigid miniature solar panels, and refrigerated photovoltaic cells. So this comes from here, right? Yeah, we want to make something as close to a leaf as possible. The artificial leaf will have these elements, right? Where is the exact nature of that? Yeah, Lewis estimates the country would need to manufacture thin films, thin solar flexible films. So it's G. The passage states that the two principal elements of Lewis's artificial leaf technology are a fuel cell and ambient air, solar electricity and a catalyst, platinum and silicon, a collector and an electrolyzer. So it's a collector and an electrolyzer, right? The two principal elements are a collector that converts solar energy into electrical and an electrolyzer that uses the electron energy to split water. So it's D. According to the passage, what is one outcome of the process of burning hydrogen in a fuel cell? The electron energy splits silicon atoms, the hydrogen bonds with oxygen, the fuel cell's lining deteriorates, the exhaust produced is water. So I think it's J because it's given here. The exhaust from burning the hydrogen later in a fuel cell is water. So it's J. Okay, so that was the 10 questions. Let's grade our answers. 31, AHCFA, AHCFA, and 36, JCGDJ, JCGDJ. Okay, great. So we got all correct. With this video, we complete the solution series for the December 2019 Form C03. All the videos are part of the solutions playlist for C03, which I would link in the description box. So be sure to check those out. Let me know in the comment section what other videos you'd like me to upload. I'll see you guys soon. Take care. Bye-bye.